Have you ever noticed how a hot mug of coffee, just cools down on its own? Or maybe felt that subtle chill near a window, even when there's no draft? Today, we're pulling back the curtain on one of nature's most elegant, often invisible, ballets, natural convection.
That's right. This deep dive is all about understanding how fluids, like air or water, actually move and transfer heat simply because of differences in temperature and, well, gravity. We're going to unpack the science behind really countless everyday things, uncover some surprising facts, and see how this fundamental concept shapes everything from keeping your laptop cool to designing truly energy-efficient buildings.
Yeah, our mission here is to take some pretty dense material on natural convection and pull out the most important nuggets of knowledge for you. Think of it as a shortcut to being well-informed, packed with those aha moments, and hopefully just enough humor to keep you hooked. Okay, let's unpack this. So let's start right at the beginning. We hear the term convection quite a bit, but what exactly sets natural convection apart from, say, forced convection?
That's a really great distinction to make. With forced convection, you've definitely got an external push, a fan blowing air, a pump moving water. Think of a hairdryer, right? You're actively forcing hot air. But natural convection, sometimes called free convection, is, well, entirely different. It's driven by completely natural means, primarily buoyancy. There's no machine involved.
And what's fascinating, I find, is just how subtle that fluid motion can actually be.
Precisely. The speeds, the velocities involved are often incredibly low. We're talking typically less than a meter per second. So this means the heat transfer isn't quite as rapid as you'd get with a powerful fan. However, the huge upside is you don't need any external equipment. No noisy fans, no power-hungry pumps.
Yeah.
That makes it a fantastic, silent, and often preferred solution for many applications.
Right. And when you start looking for it, you really do see it everywhere. From, the cooling of electronic equipment like your TV or DVD player to the way heat transfers from electric baseboard heaters or even how our own bodies shed heat. It's this constant unseen process.
Okay, let's get to the core mechanism. A classic example helps here. Imagine a hot-boiled egg just sitting there, cooling on a plate. As the egg heats the air right next to its surface, that layer of air gets warmer.
Okay, and here's where it gets really interesting, I think. It challenges that common saying. Most people say heat rises, don't they? But the source material makes it pretty clear. That's actually, well, a bit of a misconception. What's the real story?
You've hit on a crucial point. It's not the heat itself, like some abstract thing that rises. It's simpler. When air heats up, its density decreases. It gets lighter. So you end up with this thin layer of lighter, warmer air surrounded by heavier, cooler air. Think about oil and vinegar in salad dressing, the less dense oil rises. Same principle. The warmer, lighter air around the egg naturally rises.
Oh.
And as it moves away, cooler, denser air has to flow in to replace it, right? That air then gets heated, becomes less dense, rises. And the cycle just continues. This constant circulation is what we call a natural convection current, and it dramatically enhances how effectively heat is transferred, way more than if heat just had to slowly conduct through still air.
So if it's the heated air rising because it's less dense, what's the fundamental force actually driving that upward movement?
That's the buoyancy force. It's the upward push a fluid exerts on anything immersed in it. It's equal to the weight of the fluid that gets displaced. This is pure Archimedes' principle in action. It's why ships float. Why smoke? Well, hot combustion gases rise up a chimney.
Yeah.
And really critically, without gravity, say, out in space, there's no weight difference, no buoyancy, which means absolutely no natural convection heat transfer, none at all.
Wow. No gravity, no convection. That's fundamental. So, okay, we want to get a bit more technical. How do engineers actually quantify this? Is there a way to measure the strength of these invisible currents?
Absolutely. Just like we have the Reynolds number for forced flow, which tells us about inertia versus viscosity, for natural convection, we have its own key dimensionless number, the Grashof number, GR. Think of it like this. It represents the ratio of that buoyancy force, the thing making the fluid want to move to the viscous force, the fluid's internal friction or stickiness holding it back.
Okay, so buoyancy versus stickiness.
Exactly. A high Grashof number basically means buoyancy is winning that tug of war. It indicates strong buoyancy forces relative to the viscous forces, leading to more vigorous natural convection currents. For example, on a vertical plate, if the Grashof number gets above about 10 to the 9, the flow typically becomes turbulent.
Right, and I saw we combine the Grashof number with another important one, the Prandtl number, to get the Rayleigh number. Brad, what does this master number, the Rayleigh number, really tell us?
The Rayleigh number, RA, is essentially the key parameter for natural convection heat transfer. It combines the effects of buoyancy, from Grashof, and the fluid's thermal and momentum diffusivity, from Prandtl. So most of the practical correlations engineers use to calculate heat transfer and natural convection, especially for different shapes and orientations, are expressed in terms of this Rayleigh number. These formulas are often empirical, meaning they're based on lots of experimental measurements. They allow us to find the Nusselt number, which then lets us calculate the actual heat transfer coefficient. And an important detail: all the fluid properties used in these calculations, density, viscosity, etc., are evaluated at something called the film temperature, which is just the average temperature between the surface and the surrounding fluid.
Okay, so Rayleigh number is key. It's amazing how fundamental this all is. From a cooling egg to, designing an entire building's heating system, natural convection is always there. But it's not just that it happens, it's how it happens, right? Does the shape or the orientation of, say, a hot surface really change how effectively it cools down?
Oh, it absolutely does. The geometry and orientation are critical. Let's take a flat plate again. If it's a vertical plate, the heated fluid rises pretty smoothly along its surface, creating a nice, predictable upward current.
Okay, makes sense.
But for horizontal plates, things get really interesting and maybe a bit counterintuitive. If you have a hot surface facing upward, the heated, lighter fluid can rise freely away from it. That creates strong currents and pretty effective heat transfer, good cooling. However, if that same hot surface faces downward, the plate itself acts like a lid, blocking the rising heated fluid. It essentially traps the hot air underneath.
Like it gets stuck.
Exactly. It significantly impedes the convection, making the heat transfer much, much slower. Cooling is less effective. And of course, the opposite happens for a cold plate. Cooling is better if it faces down, worse if it faces up, because the cold, dense air wants to sink. We can often approximate vertical cylinders as vertical plates too, if their diameter is large enough compared to the boundary layer thickness.
So understanding this invisible dance of the air is clearly vital for engineers. And these insights allow them to create really clever cooling solutions like the fin surfaces or heat sinks we see all over electronics.
Precisely. Natural convection is often the go-to method there because it avoids noisy, power-consuming fans or pumps. It's silent, passive cooling.
But I read something surprising about that. Just adding more fins isn't always the answer.
That's a fantastic point, and it catches people out. While more fins mean more surface area, which you'd think is always good for cooling, if you pack those fins too closely together, they actually introduce too much friction for the air trying to move between them. It sort of suffocates the fluid flow.
So they choke off the convection.
They can, yes. This can paradoxically reduce the overall heat transfer coefficient. There's actually an optimum fin spacing that maximizes natural convection for a given heat sink size. Getting this right is vital because, especially in electronics, component failure rates increase almost exponentially with temperature. Just a 10 degrees Celsius reduction in operating temperature can literally halve the failure rate.
Wow, a 10-degree drop halves the failure rate. That's staggering. It definitely makes you think twice about, say, leaving your laptop running on a thick carpet or a duvet, right? Blocking those vents. And our homes are full of these kinds of applications, or maybe the deliberate control of natural convection. Take something as common as a double-pane window. You might think the air gap is just simple insulation, but it sounds like it's more complex than that.
It really is. In a vertical enclosure, like that double-pane window, the air next to the warmer inner pane heats up, becomes less dense, and rises. Simultaneously, the air next to the colder outer pane cools, gets denser, and falls. This sets up a continuous rotational motion within the gap, a miniature convection current.
And that current actually transfers heat across the gap.
Yes. It enhances the heat transfer compared to if the air were just still and only conducting heat. It's not just static insulation.
Okay, so what happens if you take that same setup, that enclosure, and lay it horizontally? Say the hot side is on top or the hot side is on the bottom. Does it behave differently?
It behaves very differently. For horizontal enclosures, if the hotter plate is at the top, well, the lighter, warmer fluid is already sitting happily on top of the heavier, cooler fluid. There's no driving force for convection. In that case, heat transfer across the gap is purely by conduction through the fluid. The Nusselt number, which measures the enhancement due to convection, is just 1.
So no extra movement.
Right. But if the hotter plate is at the bottom, now you have unstable situation. The hot Light fluid wants to rise through the colder, denser fluid above it. If the driving force is strong enough, specifically, if the Rayleigh number gets above a critical value, around 1708 for this setup, convection currents do kick in, and they often form these fascinating regular patterns called Bénard cells, almost like a honeycomb structure of rising and falling fluid.
Bernard cells.
Oh.
Interesting. So when engineers are designing these window systems, they talk about an effective thermal conductivity, right? Well, what does that capture?
That's a useful concept. The effective thermal conductivity is basically the fluid's normal thermal conductivity multiplied by that Nusselt number we mentioned. So if the Nusselt number is, say, 3, it means that due to the convection currents, the heat is transferring across the gap 3 times faster than it would by pure conduction alone. It quantifies the impact of the convection.
Got it. So putting all this together, what are the clever tricks engineers use to actually minimize heat transfer through windows? Because it seems like you're fighting both conduction, convection, and radiation.
It's definitely a multi-pronged attack. First, realize the glass itself offers very little resistance. It's the trapped air or gas in the gap that does most of the insulating work. Then, a huge factor is low emissivity coatings, often called low-E coatings. Ordinary glass has a fairly high emissivity, meaning it radiates heat well. But applying a microscopically thin, virtually invisible low-E coating to one of the inner surfaces of the double glazing drastically reduces how much heat can radiate across the gap. The effective emissivity between the panes can drop dramatically.
How much of a difference can that make?
It can be huge. For the same surface temperatures, it can reduce the radiation heat transfer component by a factor of 10 or even more, maybe up to 14 times less. Another thing is the gap width. You might think wider is always better for insulation, right? More air. But studies show that once you increase the spacing beyond about 13 millimeters, or roughly half an inch, you actually start to encourage stronger convection currents within the gap, which starts to counteract the benefit of the wider gap.
So there's a sweet spot for the gap width.
Exactly. Around 13 millimeters is often optimal. That's why some high-performance windows might even use 1 or 2 thin, transparent polyester films stretched inside the gap to divide the airspace into smaller compartments. This suppresses those large-scale convection currents. And finally, instead of just filling the gap with air, they often use heavier, less conductive inert gases like argon or krypton. Krypton is better but more expensive. These gases conduct less heat and also tend to suppress convection a bit better than air.
That's incredibly detailed engineering. And I suppose we also have to consider the window frame itself. That must be a weak link.
Definitely. Metal frames, particularly aluminum, are highly conductive. They act as thermal bridges, essentially providing an easy path for heat to bypass the well-insulated glass unit. That's why wood or vinyl frames perform much better thermally. Also, the edge region of the glass unit, right near the spacer that holds the panes apart, is another critical area. Heat transfer there is more complex, sort of two-dimensional, and often higher than in the center of the glass.
Okay, so we've got conduction, convection. But when we're talking about natural convection, especially in gases, it feels like there's another major player, radiation. How does that fit in?
That's a crucial point, especially compared to forced convection. In forced convection, the air speeds are high, and convection usually dominates, so we often neglect radiation unless temperatures are very high. But in natural convection, the fluid velocities are low. So, especially if the surfaces involved have high emissivity, meaning they radiate heat easily, the amount of heat transferred by radiation can be comparable to, or even larger than, the amount transferred by natural convection. Gases are mostly transparent to thermal radiation, so heat can just beam directly from a warm surface to a cooler one right through the gas. The total heat transfer is usually the sum of the convection part and the radiation part.
So this is why something like the surface finish, whether it's polished and shiny or dull and painted its emissivity, becomes really important in natural convection situations.
Precisely. Polishing a metal surface, for instance, can drastically lower its emissivity, significantly cutting down that radiation component of the heat loss. It's even possible, depending on the temperatures of the surface and its surroundings, for convection and radiation to work in opposite directions. One might be cooling the surface while the other is heating it. It can get complex. Now, it's actually quite rare for a real-world situation to involve only natural convection or only forced convection. Very often, they occur together. We call this mixed convection. There's a useful way to figure out which one is dominant, or if both matter. We look at the ratio of the Grashof number to the Reynolds number squared, GRRE.
Okay, green R over Re squared. What does that ratio tell us?
Think of it like this. If that ratio, GRE, is much, much less than about 0.1, then natural convection effects are pretty negligible. Forced convection is running the show. If the ratio is much greater than, say, 10, then forced convection is negligible, and it's basically pure natural convection. But if that ratio GRE is somewhere in between, maybe around 1, give or take a factor of 10, then both effects are significant. You really have to consider the combined mixed convection.
And when they're mixed like that, can they sort of help each other out or can they fight against each other?
They absolutely can do both. We talk about assisting flow. That's when the buoyancy force acts in the same general direction as the forced flow. Think of blowing air upwards over a hot vertical plate. The natural tendency for the hot air to rise assists the force upward flow. This generally enhances the heat transfer compared to either mode alone. Then there's opposing flow. That's when buoyancy acts against the forced flow. Imagine forcing air upwards over a cold vertical plate. The air cools, gets denser, and wants to sink due to buoyancy, opposing the upward forced flow. This usually decreases the heat transfer rate. And finally, you can have transverse flow, where the buoyancy force is perpendicular to the forced flow direction, like forced airflow horizontally across a hot vertical plate. This tends to increase turbulence and mixing near the surface, which generally enhances heat transfer.
That makes sense. So when engineers are designing cooling solutions, it sounds like there's a trade-off.
Exactly. For lower power devices, natural convection is often preferred. Why? No moving parts. That means no noise, no vibration, no extra power consumption, and often higher reliability because there's less to break. But for high power devices, things generating a lot of heat, natural convection often just isn't enough to keep temperatures down below critical limits. In those cases, you absolutely need forced convection, usually with fans, despite the downsides. And looking ahead, some really cutting edge research is even exploring using fluids operating very close to their critical point, the near critical or supercritical region. Down there, fluid properties like density and specific heat can change dramatically with small temperature changes, leading to potentially incredibly high heat transfer rates. It's a complex but promising area for future cooling technologies. So we've really journeyed from something as simple as watching a boiled egg cool down all the way to the intricate design of energy-efficient windows and the critical cooling of high-tech electronics. And at every single step, it all comes down to this invisible ballet of natural convection, silently driven by the fundamental principles of physics density changes, buoyancy, gravity.
It's truly amazing when you stop and think about how engineers and scientists have managed to decode these, well, hidden forces. They've created these sophisticated tools and designs that let us actually control heat transfer, making our homes more comfortable, our energy use more efficient, and our technology more reliable. It makes you wonder. Consider the vastness of space where gravity's gentle pull is absent. We said no gravity means no buoyancy, no natural convection as we know it. So thinking back here on Earth, what unseen currents might now be at play in the everyday objects all around you, silently shaping the world, transferring heat in ways you perhaps never considered before.